So hello everyone, welcome to my presentation about this algorithmic design and engineering. My name is Fodan Deng. I am a structural engineer working at the JD Architecture Design Company, Shanghai branch. And I am also a leading researcher in the research group non-structure. The non-structure is founded in 2018. And all members and all of us are either architects or structural engineers. And our goal is to bring the most advanced technology in the computer science field to the AEC field, which is architects, engineering, and construction. So here's a little info about myself. I received my PhD two years ago. Before that, I also have my master's degree in civil engineering. And in both my PhD research and my master's research, I was doing structure-related data analysis. So for example, the structure health monitoring and the corrosion monitoring. So, but after I started work in industry like 1 year ago, but when I start work, I find the way we do our work in industry, it's like haven't changed for 20 years. So despite there's a lot of new technology has been introduced to our field, but just most of the people choose to don't use it. So now I am focusing more on practical implementation of the new technologies, like machine learning or beam integration stuff like that. Okay, so let's talk about today's topic, the algorithm design. So before we speak in the algorithmic design, I think we should mention the parametric design, because I guess everyone knows parametric design. Even though you guys don't know that the term parametric design, but maybe you are already working in the way the parametric design do. So, and I guess all you guys also know the software, the Rhino and the Grasshopper. If you're not familiar with Rhino, it's just kind of the CAD software that can draw lines and draw circles and rectangular and all kinds of the geometry stuff. And about the Grasshopper, it is one of the plugin for the Rhino, and which can help you automate the geometry creation process. Let's say for the Grasshopper, if I want to create a circle in the Rhino, I can just give Grasshopper the circle components a radius. Let's say radius 3. If I only provide the Grasshopper a 3. And then the Rhino can create a circle with a radius of 3 for me. So give a set of number and a set of Grasshopper components, then a geometry can be created. So this way of creating the geometry is kind of the parametric design. And with different parameters and different setup of the components or the building logic, we can generate different kinds of geometries. Like here, I first built a shell like this, and then I changed the parameters defining the shell. Then it can create lots of different the shells with a slight difference. But the shell logic will preserved during this creation process. So the parametric design way of doing our job can help us like improve our work efficiency, because the way we build out this kind of geometry preserves the logic behind it. So I would say there will be a robust relationship between the design intent and the design outcome, because the logic is still there. Whether we change later on, there's a lot of change when we do the design. So even there's a lot of change, but the logic behind it will still be preserved when we try to do the job in a parametric design way. So for example here, if we divide the curve already into the 50 segments, then later on, if we want to shift the top of the shell a little bit back from the one on the top and to the one on the bottom, then if the curve is already split into 50 segments, then we have to modify all the 50 segments. That would be very complicated and annoying. But if we preserve the way we're splitting the curve, then this logic can be preserved. Once we move this point to the control point of the shell, then the splitting logic will be preserved. So this kind of changing will be very easy and convenient. So actually, this design approach has been widely used in the architecture projects, including the 32-meter high, the Shanghai Tower, which is the tallest tower in Asia. And we all know that in the skyscraper like this, the wind will cause a lot of problem. So usually the way we deal with it is we ask architect to create lots of different the building shape, and test each shape with the wind tunnel experiments, and then we can choose the one with the least wind impact. But if we do it in a traditional way, then we may need like 10 or 20 architects to build different kind of the building models. But if we do it in the parametric design way, since the rotation angle can be controlled only by one parameter, then we just need to change this parameter, and the building shape can change with the logic be preserved. This can save a lot of time. But there's a problem left to us from the parametric design. It's like, is this form practical or structural efficient? I mean, usually this kind of problem was answered by structural engineer with a different set of structural calculation model, which can be, this kind of model can be derived from the architect model. Then after we have the model, then we do the calculation and validate the results with there is a lot of like building safety standard or safety codes. We validate that, and if something goes wrong with that, we have to go back to the original points to change the parameter and then do it all over again. So unfortunately, this information from validation, which is like whether this building is safe enough, this information go back to the parameter change is usually done by structural engineer and architects manually. So when there's a lot of change, it's like when we need to change our design parameter a lot of times, this could be very annoying. So, but if we can somehow find a way that connect this validation process with the parameter defined behind it, with using some sort of algorithm to reflect the information from the validation process to the parametric design process, then this whole process can form a loop and thus become an automated like process. So here we can loop until the actual design is validated, then get the final result, and then we can save a lot of work. So like we don't have to go back and forth manually, like change the parameter, get the validation results, and change the parameter. So we can save a lot of time here. So this actually takes the parametric design one step further, become the algorithm design. So in algorithmic design, actually, we have to deal with the reflection problem. This reflection problem is called the optimization problem in mathematics. The x1 through xn here, you can see x1, xn here, is actually the parameter we are looking for. And the minimized goal here could be the material usage or construction cost, like something the project owner is interested in. And the constraint here may be our like the safety code, safety standards, and the space constraints, some constraints like that. So these three components will form the optimization problem that lifts us to solve. And if we can find a perfect algorithm that can do this job, and we can do it in algorithmic design way. So in algorithmic design, we have our familiar parameters, and we also have our familiar the algorithm to make the geometry from these parameters, but differently, and mostly importantly, we have the algorithm in this reflection process, like from the validation to the parameter design. And in the algorithmic design, we also need a highly cooperated architects and the structural engineer team, because the cooperation will have to made in order to like build the in-depth algorithm details. So based on this algorithm design approach, our non-structured team had developed a small application called the NS Turbo. The NS Turbo had won the first place in the AEC Hackathon in 2019 in Shanghai. And the whole idea is actually from the routine of every structural engineer, which is the floor plan change from architects. So it is said the only thing not changing is everything is changing. In our structural engineers' daily work, a lot of time we spend is on rebuilding our calculation model due to the floor plan changing. So even with a very small portion of changing, we have to go through every structural component just to make sure every component is safe and everything is not going wrong. But the more time we spend on this kind of a rebuilding stuff, the less time we're spending on thinking how can we build a better building, or how can we improve our structure efficiency. So this kind of work is the creative work. It's not just like rebuilding the same stuff again and again. Another problem is that the software we use when we're doing the structural calculation usually don't have a very good, like straightforward looking for the actual building. It is very hard to see, like, for example, if we want to see a column, like how large the column is, let's say 400 millimeter by 400 millimeter, how large the concrete column is, it is very hard it's not that straightforward to look how large is it in the structural calculation software. But architects are caring about these details, like they want smaller structural components. So this sometimes will create confusion and barriers between a structural engineer and the architects. Sometimes we have some trouble communicate and understand each other. It's like, how big is this? Is this really big? I'm not sure. Is this small? I'm not sure neither. Yeah, something like that. So for the first problem, the we want to spend less time on the rebuilding the same stuff. We just want the computer can help us to like adjust every component so that the safety standard can be satisfied. So with algorithm design approach, we would like to have an algorithm that can check the building standards and adjust the parameter by itself. So here we utilize the genetic algorithm here to solve the optimization problem I mentioned before. So a genetic algorithm consists of several steps here. The first step here is the generation of the genes. So this genes here is actually will act as parameters to generate the new models. After we have the new models here, then we will put all these models through our normal validation process. And those ones have not passed the safety code or safety standards will be eliminated by the algorithm. Then the algorithm will pick the top performance models. This performance will be based on the optimization goal, which is the construction cost or material cost. And as a last step, a new generation of genes will be created through the crossover and the mutation. The whole point of genetic algorithm is actually a mimic of a real world natural genetic the genes, like the natural evolution. They just mimic the genes, the crossover and mutation. They will preserve the best performing individual into the next generation. So but in theory, if we want to reach a optimum result, we may spend like thousands of generations or a lot of times. But in practical, it's not possible. Our time is limited. We don't have that much time to calculate models because the calculation is also a time-consuming process. But we are not trying to look for the best perform models. We just need one that can pass our safety codes and get a slightly better result, probably. So this is not that hard to achieve through the genetic algorithm approach. So it's very easy to get one result that is available to us. So for the second problem, we find the Unity is a very attractive solution here. Using a game engine in traditional CAD software seems very cool. And we also coincidentally find that the Unity is a sponsor for the AEC Hackathon event in 2019 Shanghai. So we just want to give the Unity a try on that event. And the result is actually awesome. It turned out very good. So in the last day of the hackathon event, we even implement the VR and get a small VR model into run, and that was very cool. So here's a small demo of our application. You can see our application can open a model and see this model, displays this model in different angles. You can see to show the standard floors, can set the transparencies. You can show the structural components, like the floors and the beams and the columns. They do some basic display, but in a game engine, which is very fancy, in my opinion. So the Unity is actually have a lot of potential. in doing that. So I also have several more videos to show. I'll play it one by one, so you guys just can hang on a little bit. It is also about my this team's application. So the first video here, let's see. So I may need to stop sharing here, maybe.
Yeah, probably you need to switch.
Yeah, I have to create a new sharing here. So here, okay, here. So this is the video showing the application can do the selecting work. Like you can very easily selecting some beams and some columns to set them as parameters, like the basic genius. And we also can define the parameter for the algorithm to run to set the optimization goals, something like that. And once everything is, once the setup thing is done, and we can continue to the second part, which is the automatically adjust this structure model. We can see on the right-hand side here, this is the structural calculation software. We use the API to drive it to run the structural calculation and the validation, or I mean the result evaluation. And the left-hand side here, every 1 point, I'll play the game. So every 1 point you see in the left-hand side is one calculation result. So you can see there's a lot of points. For every point, it is a calculation result. And on top of that, this is the one generation in a straight line, a vertical line over here. This is the one generation. So basically, this software can get the results and do the validation, and then based on these results, they can adjust the parameters to create a new next generation model. You see, we calculated like more than 500 models in 12 hours, even though there's only 5% material safe at last. But as long as the model is good and the design results is good, I'm happy with that. So we don't have to sit in front of the computer to watch it calculate, right? We can, like, when we go off work, we can just open the software and let the computer do the stuff, and we can go back home and sleep, and then in the next day we can watch the results. Okay. So the last video I'm gonna show is the one with the VR. I mean the third video. So the VR I mentioned before, we implemented a little bit like the small model here. You can see we rent a HTC Vive at the hackathon event. Then we pour in the Unity VR, the game object, and I mean it's a really very smooth transition from our normal programming to this VR programming. I would say that the Unity has a lot of potential in doing this fancy stuff. It is very cool. So the last one, okay, seems here I need to share it again. Okay, the last video I want to show you guys is the algorithmic design in a real world project. So this one is it is a bridge design. we did it from scratch. The first part of it is the parametric design. You can see we changed the parameter. We can change the height of the arc. After that, we can using the API to drive the calculation and get the calculation result. And then we connect the calculation result and the input parameter using the genetic algorithm. We all know the grasshopper, there's a built-in genetic algorithm that we can use. So here, that's what I use here. So basically, here we can use the genetic algorithm to finish the loop. We can use the genetic algorithm as a designing tool to help us to find the best the arc height for our bridge. With this height, we can have the smallest displacement and the best stress level in our arc. So there are about like 500 models we calculated in the 6 hours when I record this video. So it actually took a whole afternoon, but I was not sitting in front of the computer. I was in a meeting. So after I finished my meeting, I came back and I checked the results, and everything looks cool. I'll let you guys to watch it again to see how it works. So the idea is, the first part of it is parametric design, and then using an optimization algorithm to connect the output and the input of the parametric design. Then it will form a loop. It becomes an algorithm design to use the algorithm to help the computer understand your structure. It will like form a loop and give out the best results. And this is the results validation part. They can check the deflection, the stress level. And finally, we can proceed our project once everything's done. So that was pretty much everything today. So we have not yet have our website. If you guys are interested in our group, and if you guys have WeChat, we have an official account in WeChat, which is non-structured. You can follow that to receive the latest news about us. And if you have special questions about the genetic algorithm or the Unity or the other data related questions or comments, welcome to add me on Facebook. I'll try to deal with them as try my best. Okay, thanks guys. That's pretty much today, and please enjoy the hackathon event. I hope to see you guys in the future.